Hi viewers, welcome back to my channel. Today I have a problem from the topic of power screws or mechanics of power screws, and in this video I will be solving this problem from the equations that we have developed from the previous videos. So let's start to solve this problem without much ado. So here we have a power screw. It is used to lift a load of 2 kilonewton. The mean collar diameter is given. Find the torque to lift and to lower the load using a ball bearing thrust washer. What are the efficiencies? Is it self-locking? So this is the question that they had posed to us. So in case if you are worrying like, oh, they didn't give the coefficient of friction between the thread and the nut, and they didn't give you the coefficient of friction between the thrust collar and the thrust washer, you can assume it. So you can assume the first friction to be something like 0.15. This is the friction coefficient between the screw and the nut, and then you can assume the coefficient of friction at the collar interface as slightly lower value, maybe 0.02. Now, whenever we talk about the torque, I discussed this in the previous video also. There are two components to the torque. The torque has to overcome the friction at this interface and friction at this interface. Now, let's see how the expression of the torque look like. This is how the expression of the torque look like when finding the torque required to raise the load. Be very careful. It's required to raise the load. This is the torque required to raise the load. So W is the external load, dm is the mean diameter. We can equate or we can consider this as same as to the pitch diameter. Then mu divided by cos alpha, where cos alpha is the radial thread angle. See, when we had Acme threads, the thread profile was like this. If you remember, this being the axis of the screw, so this angle used to be 29 degrees, this particular angle. So that is 2 alpha is equal to 29 degrees. So alpha comes around 14.5 degrees. And another important concept is that whenever you have an Acme thread or a thread with the radial thread angle, it is as good as assuming that coefficient of friction is modified to mu divided by cos alpha because of the wedge action. Everything is discussed in the previous video. That's why you can see I'm writing mu divided by cos alpha everywhere possible because I'm working with an Acme thread. Had it been a square thread, then cos alpha is 1 or alpha is 0. Make sense? Now this is the torque. This is the component which is working against the friction between the nut and the screw, while this is the torque component which is working against the collar friction. Make sense? Now let's see how external load is known, 2 kilonewton, alpha, radial thread angle is also known. Now how we will get major diameter and all those details. That's why the designation of the screw is to be looked at very carefully. So here you can see the designation goes like this. Then we will have lookup tables in design data books. So here you see corresponding to the designated screw, these are the values for the pitch. This is a single start thread, so pitch and lead are equal. Very important. Pitch is equal to lead when we are talking about a single start thread. Okay, when you have multiple threads, then lead is equal to n times pitch. But assume that this is a single pitch thread because they didn't tell us anything explicitly, so we can assume that the lead and pitch are equal. It's a single start thread. So now we have all the dimensions here. Let's see. You have the major diameter, you have the pitch, you have the mean diameter. You can compute the cos alpha also. DC is given, the collar diameter is given in the problem. Now you know all these parameters, you can simply plug in and compute the torque required to raise the load. Coming to the torque required to lower, here you see there is a minus term here and there is a plus term here. Why? Because see, if you remember the original formula for a square thread, the torque required to raise was W dm by 2 into tan phi plus alpha, where phi was tan inverse mu, where mu is the coefficient of friction between the screw and the nut, and alpha was the lead angle, that was tan inverse p divided by pi dm, where p is your lead and dm is your mean diameter of the screw. So while torque related to lowering was w dm by 2 tan of phi minus alpha. So if you remember these two equations correctly, then you will understand why there is a minus sign here and there is a plus sign here, and why these signs are different compared to the expression for the torque related to raise the load. Make sense? So this is how you can evaluate the torque required to raise as well as lower the load. But now they are asking us how you will evaluate efficiency. See, what is efficiency? Efficiency is nothing but output divided by input. Assume that you are working with a power screw and you are rotating your power screw by 1 turn. What is the work you are doing? That is the input, right? I repeat my question, you are rotating your power screw by 1 turn. So you are applying a torque, say you are raising the load. So TR, what is the angle with which you are rotating it? It's 2 pi radian. And what's the output you are getting? If you had a load of W on top of it, that load will move by the lead, by an amount which is equal to lead of the screw. In this case, lead and pitch are equal because we are talking about a single start thread. So the output is nothing but W times P. Make sense? This is how you compute the efficiency. Make sense? You don't have to mug up formula. Just understand what you are doing. Similarly, when it comes to efficiency, when you are lowering the load, same concepts hold true. You're doing the work on an external load which is equal to W. You are lowering it down by an amount which is equal to the lead or the pitch of the screw. What amount of work you are doing? It is 2 pi divided by TD. So just check for dimensions also here. See, W is having the units of Newton, pitch is having the units of millimeter. Here also 2 pi is dimensionless while TD is having dimensions of Newton millimeter. So this equation makes sense. And I hope you understand when you have a torque, constant torque, the amount of work done by the torque is nothing but the torque value multiplied by theta, or in other words we can say that's integral T d theta. So in this case we assume that the torque is constant and the work done is T into theta 2 minus theta 1. This integration limits going from theta 2 to theta 1. So now we have the efficiencies also. Now let's look into the last portion of the question where they are asking us whether the screw is self-locking or not. Very important, whether it is self-locking or not. So for a screw to be self-locking, that it means we need to apply a positive torque to lower it. On its own, it won't come down. It's good, right? You think of a jack, a screw jack that you are used to remove in your automobiles to replace your tire. You don't want your screw jack to come down automatically. So in that case, we need self-locking screws. So that means your TR should be greater than 0. The torque required to lower the load should be greater than 0. Or in other words, for a square thread, it is mu greater than P divided by pi dm. Or in other words, this is for a square thread. In a minute I will modify this expression for a Acme thread. This is the equation for a square thread. But when you come to an Acme thread, I told you it is as good as replacing the coefficient of friction with mu divided by cos alpha. Because of the wedge action, there is an increased friction at the interface, and this should be greater than P divided by pi dm. Again, all these things are known to you. The coefficient of friction we assumed, cos alpha is known to you, pitch is known to you, the mean diameter is known to you. Mean diameter is equal to your pitch diameter also. So you can plug in all these values and check whether the screw is self-locking or not. So in a nutshell, using equations are fairly easy. We have two expressions for the torque required to raise as well as to lower the load. Then we discussed about the concept of efficiency when we talk about power screws. Finally, we checked whether the screw is self-locking or not. So thanks for watching. I hope you understood all these things in a very good way. Thank you. Thanks for watching.